So welcome to the deep learning course. I'm going to split these 2 hours into two 1-hour lectures, and we'll take a short break in the middle. And I'm going to start by giving you an overview of the course structure and the assessment and those bureaucratic parts. And then I'm going to talk a bit about the deep learning in the context of artificial intelligence, give you a brief historical overview of how these things developed, and talk a bit about machine learning, so a brief review of what we did last semester, but to give you the idea of what is special about deep learning and what deep learning can offer in, that is different from those classical machine learning approaches we saw last semester. And then in the second hour, I'm going to try to convince you that this is true, what this promises here. So the objective of this course are to give you some knowledge, theoretical knowledge and practical knowledge on deep learning. So these foundations of neural networks, the activation functions, the optimizers we use, how to train the network and to implement different architectures. Talk about these different architectures and what they are used for. So dense networks, convolutions, recurrent networks, using networks to generate examples. And then some practice and theory on how to train and regularize the networks, and basically get some experience with Tensorflow and Cabbage. At the end of the semester, there will be one lecture about PyTorch, but we're going to focus on Tensorflow and Cabbage. That is what we use here on this course. I'm going to be teaching the lectures and the P3, the third practical class. Professor Claudio Soares has the other two classes, P1 and P2. And the assessment is similar to what those of you who did machine learning last semester, it's the same general idea. You have two written tests that contribute to, that make up the theoretical component, that's 50% of the grade, and can be replaced by the exam. So the exam can substitute this 50% part of the grade. You also have two assignments in groups of 2. This is the lab component, that is 50% of the grade, and will not change with the exam. So you have whatever grade you have at the end of the semester at that. You also need at least 9.5 out of 20 on each of these components. So if any of them is lower than 9.5, you cannot approve the course. Tutorials start next week, so they are on Thursday and Friday, so they start on the 17th, on Thursday next week. All the information you need about this course is on the course site. You'll have access to the lecture notes, the exercises, the files for the exercises, the slides, and if everything goes well, the recording for the lectures. These are recommended books that you can read to go deeper into the subject matter, although the level of detail that you need to know for the tests is what you can get from the slides and the lecture notes that you have on the site. However, I recommend that you look up the references. Sometimes I recommend specific chapters of books because they help you, if your understanding goes a bit deeper, it helps you have a clear idea of the concepts when it comes to the test. And if those of you who took machine learning last semester know that the kinds of questions that I make are about explaining things, so you really need to have a clear idea of the concepts in order to answer it properly. We're going to use Python and TensorFlow, so the easiest way of getting this is to install Anaconda. If you already have it from last semester, just use that installation, and you can install TensorFlow on that. This will give you all the libraries you need for plotting, for NumPy and things like that, scikit-learn also sometimes for processing data, and TensorFlow includes Cabbage too, so this way you'll have everything you need for this course. Okay, so let's start with taking a broader look at artificial intelligence in general. And although the idea of having thinking machines has been in fiction for quite a while, the modern scientific approach to artificial intelligence we can consider to have started in 1956, when some top scientists gathered together and decided to take a few weeks to solve this problem of how to get a computer to think like a human. So computation, mathematics, and so on, they thought this would be fairly easy to do. It turned out to be a bit more difficult than they estimated at first, but this was the first step to try to make the computer think. And so the idea here is that if we can precisely describe what intelligence is and what learning is, then we can put a machine to actually simulate it so well that it's the same thing as doing it. And this was what the initial success of artificial intelligence came from, was in explicitly programming intelligence into the systems. So we have rules, we have inferences, we have these kinds of expert systems based on logic programming and things like that. And they made the computer simulate the inferences that humans can make. One example is this MySim system in 1975 that was used to diagnose, to identify bacterial strains based on some features. And the system not only identified the strain, for example, in this case, 70% probability that it's a streptococcus, but it also managed to point out what were the reasons for concluding this. So it's gram-positive, the staining, it's a coccus, a spherical shape, and it grows in chains. So given these three, there is a 70% evidence that it's streptococcus. So this was the beginning of AI, mostly focused on explicit inferences, on reasoning, but making the computer follow these logical steps, just like we do when we are explicitly reasoning out something. But in parallel, we also have, since 1943, this attempt to try to model how the brain works, or how the nervous system works. So, in 1943, this McCullough-Pitts model of the neuron tries to represent how the neuron works mathematically. The neuron is a cell that has this long arm, this axon here, and basically we can think of these dendrites as receptors. They feel some stimulus, and if the stimulus is too small, the neuron simply ignores it. But if the stimulus passes some threshold, even by a tiny bit, then the neuron suddenly fires. So there is a depolarization of the membrane that spreads through the axon, and then there is a release of neurotransmitters in the synapses here. So this is a non-linear response. If the stimulus is not enough, it's zero, but if the stimulus passes the threshold, then it fires everything it's got. And to model this, what McCullough and Pitts proposed is that we consider the stimuli to the dendrites to be a vector of numbers in abstract. The sensitivity of each dendrite, of each receptor, is modeled by a weight. And so what we do is we multiply each input by the corresponding weight, and we add all these combinations. So this is a weighted sum of the inputs. And now we pass this weighted sum by a nonlinear function. For example, a threshold function that outputs 1 if it's greater than some threshold, or 0 if not. And this way we can mimic this nonlinear response of the neuron. So in theory, we could use this to, by adjusting the weights, to have the neuron, say, distinguish between different shapes or different types of objects or something like that. The problem is, how do we determine the appropriate weights for this? And this appeared in 1958. Rosenblatt proposed the perceptron, which combined this mathematical model of the neuron with an update rule that allowed it to learn from examples. You give examples and tell it if it's wrong or right, and it will adjust the weights until it gets everything wrong, everything right. Sorry. And this was appeared in the New York Times as the embryo of a computer that would learn to talk and walk and reproduce and think and so on. And so everyone was very excited by this advance in artificial intelligence because of this training rule. So this is the neuron. We have all the inputs multiplied by the corresponding weights. We sum everything, the weighted sum. And now we check if this is greater than 0 or not. In order to be able to adjust the threshold, there is an additional parameter here that we can increase or decrease so that we make it more or less sensitive when firing. But anyway, this is the nonlinear response of the neuron. The way we are going to update the weights here is to check if the output is what we want. So we check the difference between the target, the desired output, and the actual output of the neuron. Do you have any question there? Do you have a question? So if there is a difference here, we are going to make a small adjustment to the weight. And the adjustment is a small fraction of the difference multiplied by the value of the parameter that comes here. So if it's a large value coming through that weight, we have to adjust the weight more. If it's a small value, we adjust it less. And we are going to adjust it based on this difference so that if the target is above the output, we are going to increase a bit the weight. If it's below, we're decreasing, or we change the sign if the input is negative and so forth. So this works by this tiny adjustment. It allows us to slightly correct the parameters of the neuron each time there is a mistake. And by doing this, we can just show examples to the perceptron, correct things each time there is a mistake, and eventually it starts making fewer and fewer mistakes. So this was first implemented in this IBM 704 computer, and it learned to distinguish between these punched cards, that some of them were punched on the left side, some on the right side, and eventually the perceptron learned to tell them apart. But it was then actually built as a machine. So you have this camera with 400 pixels, 20 by 20. They are all connected by wires to these potentiometers that adjust how sensitive the system will be to each input, to each pixel. And the potentiometers had electric motors that were automatically adjusted when there was a mistake in the classification. And using this, they managed to train the perceptron to tell apart different simple shapes, circles and squares and things like that, showing to the camera, and it managed to distinguish. So this was a huge advance because the machine could actually learn. You don't have to program it explicitly, just show it things, and eventually it learns to do what you want. But the problem is that the perceptron is just a linear model. What we're doing here is taking a linear combination of the inputs and then making a decision. So this can only properly separate different classes if they are linearly separable. If we can find a linear frontier in the dimension of the input that can separate the classes. And this is mathematically equivalent to linear classifiers that already were known, like logistic regression. And if you have some data set that is not linearly separable, the perceptron cannot learn to separate them. So the best it can do is to make fewer mistakes, but it will not learn more than this. So this was a big disappointment because it's basically logistic regression but trained differently. It's the same model where you have a linear combination of the inputs and then you have a non-linear activation function and you determine the inputs to minimize the error. So it's exactly the same thing, and logistic regression was already well known by the time perceptron was invented. So this led to what was called the AI winter, which was after that enormous hype about what these things could do. It turned out that they didn't do anything new because it was exactly the same as all these systems that were already known. So in the 60s through the 80s, there was this disappointment with artificial intelligence, AI winter, and there were mostly logical systems in artificial intelligence during this time. For example, Prolog for programming with explicit these declarative rules, and which then led also to things like SQL and things like that. So these declarative languages are still used. So this was the main thing behind artificial intelligence. Yeah?
What does ANN stand for?
Sorry?
What does ANN stand for?
This is artificial neural networks.
Okay.
So neural networks were in particular a big disappointment at this time. But there was this 1969 paper by Minsky and others on perceptors that showed they didn't do anything new. They actually also demonstrated that if we could connect several neurons, then we could go beyond this simple linear classification. The problem is then, how do we compute the weights? Because that update rule works for a single neuron, it doesn't work for a network. But during the 70s, this backpropagation algorithm was already applied to other different fields, and eventually they figured out that they could apply this to training artificial neural networks. So in parallel, also in the 80s and 90s, there was some, especially in the 90s, big advances in machine learning other than artificial neural networks and logic. So the kind of machine learning that we saw last semester. This is the basic idea, that we want to create a program that can improve at some task when we give it experience, when we give it examples. So that we don't have to explain exactly how to do something, but we can show it when it's done correctly or incorrectly and give it that feedback. So basically, we need to have this task defined, the measure of the performance, and the data that we use to improve the performance, but this can be many different things: image classification, spam filtering, etc. And this will be used in different contexts. For example, in unsupervised learning, we basically have a set of features and we want our learner to give us a new set of features. We can do this with dimensionality reduction and have a more compact representation with principal component analysis or something more sophisticated. We can do this with clustering and have additional labels that tell us which examples belong to the same group or to different groups, this kind of thing. Or we can do this in the context of supervised learning, where in the training data we have the target values, and we can ask the system to try to predict correctly the target values. So we can use that error between the prediction and the target to adjust things and to guide the parameters of the learner. We can have combinations of this, where some data is labeled, others unlabeled, or a slightly different problem with reinforcement learning, where we have a way to evaluate the output, but this may not match precisely each decision. For example, if you're training the computer to play a game, chess or something like that, you can tell it lost the game or it won the game, but you cannot tell exactly which move led to that, because it's the combination of moves that lead to victory or defeat. And so the problem now is to try to assign credit to all of those decisions based on the results that we are getting. So this is a slightly different problem. Yes?
I have a question. Are those all backpropagation algorithms or just the reinforcement one?
Now, the backpropagation algorithm is used to train artificial neural networks.
Okay.
And you can do all of these with artificial neural networks and backpropagation. But you can also do these things in different ways with other learning systems that do not use backpropagation. For example, you can train a single neuron with backpropagation that works exactly as logistic regression. Or you can train it by solving the equations as you do it in logistic regression. So there are different ways. Backpropagation is one way of training the net. So this is an idea that, the basic idea here is that using different models and different algorithms, we could solve different kinds of problems in this way, not explicitly telling the computer how to solve it, but by creating some algorithm that would learn to solve the problem given the examples. And so we can use that to extract new features, to predict something, to optimize decisions, and so on. And the traditional approach in machine learning is to use different algorithms for these different examples. Clustering algorithms, support vector machines, nearest neighbor, things like that. You can see the kind of approach here. So these are actually old methods, linear regression from the 1800s, this logistic regression in the early part of the 20th century, and so forth. And the idea here would be that humans decide which features to use. We have some problem, lots of descriptors of our data, but we pick out the ones that are more informative. And we have some linear model, either for regression or classification, that does what we want. In the 1990s, one thing that greatly changed these conditions was the things like the kernel trick for support vector machines, which made it very easy to do this nonlinear transformation on the data. As you saw last semester, if we have a problem that cannot be solved with a linear model, but if we change the data properly, we can turn it into a problem that can be solved linearly in the new space where the data lies. So with the kernel trick in support vector machines, this can be done very easily without much expensive computations. And so now we have a huge increase in power for solving these problems, regression and classification. But we still have the problem of choosing the right features and then feeding them to the algorithm and then choosing which algorithm to use and so forth. In parallel, we also have some advances in neural networks for example, processing checks and identifying handwritten digits for postal code processing, these kinds of applications. And this big change is because of the power of these nonlinear transformations. If you have a linear classifier, it can deal with cases where the classes can be separated by a linear frontier. For example, with logistic regression, because even though you have this output function that is not linear, the input is a linear combination of the data multiplied by this weight, so you cannot do something that bends, create a frontier here that is twisted. It's always a straight line. But what you can do here is, instead of using the original data in this two-dimensional space, for example, in this case, you cannot, using a logistic regression, which will predict the probability of the points belonging to one of the class, for example, the red class. This is over here the probability is 0, over here the probability is 1. But since this is a function of a linear combination of the coordinates, this part will always be a straight line here. So if you have a more complicated disposition of points, for example, like this, then you cannot use logistic regression in this data set to do the separation. But as we saw last semester, what you can do is to do some nonlinear transformation. For example, we add a new coordinate that is the product of the other two, and now our data will be distributed in a bent surface in this three-dimensional space. And if we now cut it with a straight plane in this three-dimensional space, because the data is now bent, we can create this kind of frontier in the original space. Not because of a change on the classifier, it's still linear, because of the way we twisted the data in order to accommodate this problem. And we can do this whatever by whatever amount we want. We can increase the number of features there. So this is the power of this nonlinear transformation of the attributes, which can help us convert a problem where we cannot solve with a linear model into a problem that can be solved with a linear model in this new higher dimensional space. So support vector machines can do this very inexpensively, because what a support vector machine does is not look at each individual data point, but look at the inner product of vectors in a way that if one of the examples is surrounded by examples of the same class, then that one will be ignored. The multipliers here will tend to 0, because that one is irrelevant for classification. So if you look at this problem here, these points here don't really matter for deciding where to put the frontier, because all we care about is this region here where they are close together. So looking at this inner product of the examples, we can decide where to place the frontier optimally away from the closest examples. But we can compute the inner product of some complex transformation of our vectors by using these kernel functions that simplify this computation. For example, this is the example of a kernel for a polynomial expansion that can turn a vector of, say, 2 elements into a vector of 12 elements or something like that with a polynomial expansion. But if we want to compute the inner product of 2 of those vectors transformed, we just need to compute the inner product of the original ones, add a constant, and then raise to the power of the polynomial we're trying to use. For example, in this case, a power of 2, power of 3, whatever we want. And this is a lot less expensive than actually extending and creating all of those new features. So since we can do this implicitly in the support vector machine, we now have enormous power for twisting all of these discriminants in the original space. We're still doing a linear classification somewhere in the more complicated space after the transformation, but we don't even need to do the transformation explicitly. It's all done for free with this kernel vector. So this was a big advantage. Support vector machines and kernel methods in general allow us to twist the data at will. All we need to do is to decide what kind of kernel to use and then apply it to our data. Of course, the problem here is that the greater the power we have, the greater the chances of overfitting. So in general, there is this no free lunch theorem for optimization problems, which tell us that on average, all algorithms work the same, have the same performance over all the possible data sets, the mathematically possible data sets. Because if it performs better on some particular type of data, there is some way you can put the data in that will deceive the algorithm and make it perform worse. You can also see this, for example, in game theory. There are lots of games where having a strategy that you are following can make you vulnerable to someone knowing that strategy and taking advantage of you. So if you're playing rock, paper, scissors, the best thing to do is to play randomly. Because if you have some scheme for after rock I play scissors or something like that, then if the other person knows, you're always losing. So this is the general idea for optimization problems in general. If it's good at some kind of data, it's bad at some other kind of data, and on average, everything is the same. Of course, this is an average over all the mathematically possible data sets, and the real data is not all the mathematically possible data sets, because reality doesn't allow for everything. So in practice, there are some things that work better than others for actual problems. But this is important for two reasons. There is no single model that you can use that is better in all situations, better than all the other models. And there is always the problem of overfitting. So if you use the model with a small training set, for example, then it may be learning things that don't generalize. So my youngest daughter gave me a good example of this recently. She learned about Portugal and Spain and the Iberian Peninsula, and in the geography test, it asked her what is a peninsula, and she said it's a set of two countries. So she actually learned a characteristic of peninsula, but it's not the one that generalizes for all peninsula. This is an example of overfitting when you have very incomplete data. So these are two problems that mean you cannot simply say, okay, I'm going to use support vector machines with a Gaussian kernel on every problem. Sometimes it will work, sometimes it won't, and you need to have different models for different problems. So basically, nonlinearity, this ability of doing nonlinear transformations is important for capturing the patterns in your data, but if you go too far, you may reach this problem of overfitting. You learn things that don't generalize outside the training data. And this is basically what we saw last semester. As you increase the power of the model, you decrease the error on the training set, but eventually you start increasing the error outside the training set because you're learning the wrong things about the data. So we need to be able to adjust the models, measure this overfitting, and adjust the way we train and also the model itself so as to minimize this problem and try to make it perform as best as possible outside the training set. Okay, so these are the kind of things, to sum up, that we want when we use machine learning. We need these nonlinear transformations to add power to our models. Otherwise, if we just have a linear model and do everything linearly, there's a lot of problems where we'll have very poor performance. But we need to be able to get different models and pick the best one for each particular problem, because they will not be good in all conditions, in all data sets. We also need to have the right features in our data. If we are using the wrong features, then the model will not work very well. We need to be able to prevent overfitting. This is also related not only to the way we train the model, but also to the model we select. And currently, one thing that is desirable in most applications is the ability to use large amounts of data. So, for example, if you look here at the support vector machine, you can see that we have a problem here, which is what we're trying to optimize is the inner product of pairs of examples in our training set, and we are doing this over all the pairs of examples. So as you increase the data set, the demands here increase quadratically. So support vector machine is very good, but if you have a huge data set, then you need to adjust the technique because it won't work with a very large data set. So this is something that is also generally desirable, not only because we currently have increasing amounts of data, but because using more data tends to allow for more powerful models, because we reduce the risk of overfitting, the risk of having things in the data that do not generalize. Okay, and what deep learning allows us to do is basically solve all these problems. I'm going to talk a bit more about it after the break, but we have these nonlinear transformations for free. We can stack them as many as we want. We have many different models because we can adjust the architecture of the network, but they are all basically the same thing. It's like playing with Lego. You have the same pieces, but you can do many different constructions, and they still work all basically in the same way. The model itself can learn how to pick the right features, so we don't have to do this pre-processing ourselves. We just put in the wrong data, and as long as we have enough data, the network can learn to pick the right features, which help us prevent overfitting, either by fine-tuning the complexity of the network or by using regularization methods that are always the same, because it's always networks of neurons. Doesn't matter if it has more or fewer, we can use basically the same regularization methods. And the way these models are trained, by presenting examples and doing small adjustments to the parameters, allow us to deal with any amount of data that we have. We just keep presenting the examples. So this is basically what we gain with deep learning. So to sum up this first part, I gave you just a brief overview of the course, and this is the context here in artificial intelligence, these disappointments that led to a long break in research, especially in artificial neural networks, but then the backpropagation and this realization of the power of the nonlinear transformations led to an increased interest in artificial neural networks, and more recent advances that I'm going to talk in a moment led to deep learning starting to have a big success. So this is basically the promise of deep learning that I'm going to try to justify in the next lecture. I recommend that you read this chapter 1 of Stancy's book and chapters 1 and 5 of deep learning for a bit more about these parts. And just stop the recording now.